conversion of kinematics quantities into vectors. Now we've used into vectors. We've done a little bit of the vector character of the kinematics quantities like displacement, velocity, acceleration by having positive or negative velocities, displacements, accelerations. However, when we translate this into a two-dimensional framework, we're not only going to need positives and negatives, we're going to need some other way to specify which direction we're going in a two-dimensional plane. This can be done a couple of different ways. We'll get into that in a minute. But the point here, what I mean by that is we might express displacement as a vector. And the displacement, do position first. So we can express position as a vector. Now, a lot of times position as a vector, it's expressed, you put an X, that just means position, could be an R. And what you do, initially position was just either an X or a Y. It goes to the vector form. And basically what you have when you have a vector is you have an X component and a Y component. Now, what this is saying is it's saying object located at coordinate X comma Y in the coordinate plane. That's what this is saying in vector form, okay? Now, the coordinate where an object is located is going to depend on what you've defined as zero. And for different physics problems, you define zero in different ways. A more common vector that you'll use is displacement. And basically, again, displacement, what you have a vector form, and then you will have, sorry, this should be delta x in vector form. You will have a change in your x and a change in your y. So both of these things are included in displacement. And basically what we're saying is that this is the x component of displacement. So the way you can think about it, it's how much the horizontal has changed in this displacement reading you're given. So x component of displacement. And then the delta y would be the y component of displacement. All right. When we talk about velocity, what we were using before, we were just using a v for velocity. If we have a velocity vector, the way this will be written, we'll have an x component of velocity and a y component of velocity. So the idea with this is that when you have a velocity vector, you're going off in some direction. And the idea is that you're going at some rate in some direction. And you can express that as the rate at which you're going horizontally and the rate at which you're going vertically. You're going, when you're going in, a two-dimensional plane, you'll be going, you're traveling at some speed horizontally and some speed vertically. Now, you're not doing those separately. You're not breaking those into pieces, but you can think about the direction you're going as having a horizontal component and a vertical component. Now, another way you can think about this, if you're going, from, I don't know, let's say from Pocatello to Denver, you would, and let's say you were going in a straight line. You can't, but let's say you were. You would go southwest. Now, as you're going in a straight line southeast, as you're going in a straight line southeast, there is a rate at which you are moving south and a rate at which you are moving east. That's what v sub x and v sub y are telling you. They're telling you the rate at which you are going southward and the rate at which you are going eastward, or x would be east-west in a cardinal coordinate plane, in a map coordinate plane, and y would be north-south. So that's the idea with that. You could do this with final velocity. So you would have v final of x, v final of y, and then you could do that with initial velocity. You would have v initial of x component and v initial of y component. And you can also do this with acceleration. You can have your acceleration be written as some x component of your acceleration and some y component of your acceleration. A little less common with acceleration. We typically construct kinematics problems such that one of those is 0, but we'll get into more of the nitty gritty a bit later when it comes to that. Now, this is going to be a bit of review, but I do want to go over it. And the idea is that a vector quantity can be given in rectangular or polar form. Okay. Now, the rectangular form, we're going to do we'll do a position vector in rectangular form. So what we would do is we would say, okay, we have this vector, and then we're going to say, okay, it's 6 meters and 8 meters. Now, if it's written like this, basically that first number is telling you the x position, and the second number is telling you the y position. So this is no different than writing that in a coordinate plane. So, or writing that as an ordered pair in a coordinate plane. So if we go by twos, 2, 4, 6, 2, 4, 6, 8. Those aren't quite evenly spaced, but no big deal. And the idea here is that if we wanted to get this, what we would do is we would go 6. So that would be our 6 meters in the x direction. Okay. And that's what that first number is telling us. Now, the second one is telling us, okay, once we do that 6 meters in the x direction, we're also going to do 8 meters in the y direction. All right. So those are the two vector components of this vector x that we're dealing with. Now, the vector x starts at the origin, and it points to the head of the combination. So this would be the vector x, okay? So that is a visual display of vector x. All right. So that's what we mean by vector, the position vector x in this case. Now, and this is expressing x in rectangular form. But we can also express x in polar form. And what polar form involves? It involves a magnitude. And the way you can think of a magnitude, at least visually, is it's the length of the vector. So I've drawn that arrow x, and the magnitude is going to be how long that arrow is. And then the other part of polar form is the angle. You need a magnitude and an angle. And basically what the angle is it's the angle from the positive x-axis. Okay. So when we talk about magnitude, the way we would write that, you can write this a couple of different ways. The one of the most common ways is that you write it. This is explicit. This is saying magnitude of x. So magnitude looks like absolute value. You put absolute value around a vector. That's saying the magnitude of x. Now there is a shorthand, and that is to simply just write it just x without the vector. If it's understood that x is a vector, if you write it without the vector symbol, a lot of times what you're indicating is that you're just talking about the magnitude of that vector. Sometimes that's all you care about, but you're talking about the magnitude of the vector. Okay. That is more open to confusion, but so if you're unsure about what to use, then use the absolute value with the arrow over it. Okay. Now, if we want to find this, if we want to find the x, the magnitude of x, what we're going to, and the other thing is that this is sometimes the other reason this can sometimes get confused is that it's unclear if this is the magnitude of the vector x, of the position vector, or if it's the x component of the position vector. So I'm gonna leave that alone for now, and I'm just gonna say the magnitude of x. And basically what we're going to do is that in order to find that, that'll be 6 squared. So that's the x component squared plus 8 squared, the square root. Now, how did I get that? Well, the idea here is that x in this picture is the hypotenuse of a right triangle. So it's just equal, what we have is x squared equals 6 squared plus 8 squared. Okay. And that's what's going on with that one. And when we do that, when you find this one out, you find that that is equal to 10. Okay. So basically what you're saying is that the length of this vector is 10. All right. Now, the other thing we want is we want the angle. Now, if we go back up to this thing, the angle would be that angle right there, measured from the positive x-axis. And again, this horizontal line to the right, that is the positive x-axis. Now, in order to do that, we have to remind ourselves that tan theta is equal to, no, it's 8 over 6, not 6 over 8. 8 over 6. Okay. And when you do this, you can use an inverse tan function, so, or an arctan function, it's the same thing. So arctan of 8 over 6, when you find this, you will get 53-ish, 53.1 something, but so approximately 53 degrees. Now, here is the thing. I strongly encourage you to just do a reality check on your angle. Okay. So go ahead, plug that in. You will see that you get, if you do this, you get 53 degrees. Now, you might not be able to tell if you've done it right, especially if your scaling's off, but just does 53 degrees make sense? Is it in the ballpark? Because here's the thing. What if instead, I'll do this in blue and purple, we had -6 and then switching to purple. Oh, whoops. -8. Okay. So basically in the opposite directions. And I'll do this. I guess I'll do this in orange. And we had, we'll call this, I don't know, x2 vector right there. Well, here's the thing. The angle you would be looking at, you'd want, would be this angle right here. But if you do that, change to orange. If you try to do that where you have arc or inverse tan, and you do -8 over -6, notice what happens. -8 over -6 is just going, then your negatives are going to cancel. And you go ahead and do that, you will find it gives you 53 degrees. That is wrong, okay? Look at this angle. There is no way that the angle of this orange vector I've drawn is only 53 degrees. The point is that arctan functions are only going to give you, they're only going to give you quadrant 1 and quadrant 4 answers, okay? They won't give you quadrant 2 or 3 answers. And sometimes your angles will be in quadrant 2 or 3. All right, so this is false. And the way you can do that is you can do a reality check. You can say, well, I know that vector is pointing into the third quadrant, but an angle of 53 is not a third quadrant angle. It's a first quadrant angle. If you end up with that case, what you need to do is you need to take the 53 and add 180. Okay. When you do that, you end up with 233. All right. And that is the angle. That is a third quadrant angle, 233 degrees. That is a third quadrant angle, and that one would be fine. Now, here's the thing. It's going to be a little bit off. And I'll indicate why this works. It's going to be a little bit off because of the rounding when I rounded the angle. But if you take the actually, this one will probably be the same. If you take tangent of 53 and tangent of 233, you will get exactly the same answer, okay? The tangent function, it gives you an output of the same if you're using 53 degrees or 233 degrees. And the point is that the arctan function, it doesn't know that when it's doing the inverse, it doesn't know which answer you want, 53 or 233. So it will always just give you the 53. It's on you to decide if you want the 53 or the 233. Okay. So that's all I'm going to say about that, but you got to be real careful with that one. All right. The a couple other things I wanted to talk about. The way you can think about this, this position vector, or if it was a displacement vector, you could think about, okay, if we so displacement vectors. The idea is that if you have a vector, a delta x vector of 8, 6, like, we used the position vector before. You could take this to mean first displace 8 in the x. And then you could say, then displace 6 in the y. Now, that you can combine your vectors in that way, or what you could mean is you're displacing 8 and 6 in the y at the same time. So it could mean you're walking along that diagonal path. And you could be walking along any path to get to this final displacement. So that is one of the ways that you can think about having displacement vectors. The point is that they will combine in that way. If you first displace 8 in the x and then displace 6 in the y, this will be your final displacement. Okay. Now, this can come up. You can also velocity vectors can be combined. So velocity vectors can be combined. Now, the situation where this comes up is if you have a moving object in a moving medium. For example, if you have a river, let's go to blue. You have a river and you have a purple sailboat. The river is flowing this direction at velocity of the river. Okay. And then you have a purple sailboat and you put it perpendicular to the bank and you set it across at a velocity. You aim it directly across with some velocity of the boat, v sub b. Well, the point is that your net velocity will be the combination of these two things. It will be the velocity of the boat plus the velocity of the river. Now, ultimately, what happens is because these two things are perpendicular, kind of what this will look like is, as we have it, the velocity of the river is in the x direction. So this will be velocity r in the x, and then velocity of the boat in the y. That is your overall velocity, okay, of this boat. And you can see that, if you wanted to get directly across the river, you'd have to aim the velocity of the boat upstream a little bit, such that its horizontal velocity would cancel out the velocity of the river. That's the idea. Okay, so that's what's going on there. This brings up the idea of adding vectors. So I want to talk about how we can add vectors. So adding vectors graphically. Now, what I'm going to do is I'm going to go grab some of the pictures I used and put it into the notes. Maybe. All right, there we go. Okay, so if we have three vectors that look like this, A, B, and C, and we wanted to add them all together. So we wanted to get, A plus B plus C. Well, what we could do, this is the head to tail method. And I'll kind of show you what we mean. So first, if we wanted to add B to A, what we do is we'd start with A, and you can see this A is measured as 25 meters, B is measured as 23 meters. But we'd start with A, and then what we'd do is we'd take the vector B, we'd start from the head of A, and we'd put B's tail on A. So approximately it would look like this. Now it's not perfect, that's an approximation, but approximately it looks like this. And if we want to add C to that, we start at the head of B, and that's where we put C's tail. So it looks something like this. Okay. And then the sum of the vectors, we'd start from our first vector A, and we draw an arrow to our final vector C. I should do this with those three. And so this sum that I've drawn here is A plus B plus C. Okay, so that is how you combine those things vectorially. Now, the issue with doing this, and I'll show the book has a couple more pictures, but I'll bring those in as well. The problem with doing it this way is that so there's the first one. Well, that's kind of how you set that up. The problem with doing it this way is that I'll show this in the next picture. Is that basically the way you figure out your resultant vector is you would have to do something like this. Whoops. You'd have to do something like this. You'd have to measure the length and the angle of the resultant vector. Now, if you've done your vectors correctly enough, like if you've been really precise about their locations, their angles, this is doable. But it's less than optimal. Okay, so there is an analytical method which we'll get to in just a minute. But before I do that, I want to talk about vector subtraction. Oops. And there are basically two ways you can do this. You can do the flip method. And so the idea here is that if I've got two vectors, we'll just look at these as vectors A and B. So I'll have A going up like so, and then B going horizontally like so. Now, as a reminder, if I wanted to do A plus B, basically what I'd do is I'd first write A, and then I would do B, like so. So A and then B. And then I would do the tail, change colors. I would do the resultant vector. This thing would be A plus B, just like that. Oh, one other thing. Important thing to know is it doesn't matter which order you do this in. I'll put one more thing into the notes just to show that. But it doesn't matter. Whoops, move it over. This third image I'm bringing in right here, it can show you, okay, basically this one, what they did is they did C, then A, then B. And notice you get the same final vector, like this vector right here is the same as this vector right here. So the order doesn't matter when you're adding. It does when you're subtracting, but it doesn't when you're adding. Now, getting back to subtraction, what the flip method is going to do, basically what you're going to say is you're going to say A minus B is equivalent to the vector A plus the vector negative B. Now, negative B is the same length as B, just in the opposite direction. Okay, so if I have B like so, then negative B is going to start from the same point, going to be roughly the same. Well, not roughly, it should be exactly the same length, but roughly when I'm drawing it freehand, but in the opposite direction. Okay, so if I wanted to do A minus B, basically what I'd have is I'd start with A, just like before, but this time, instead of drawing B to the right, B now goes to the left. Okay, so it looks like this. Then what you do is, again, for the final one, we'll change to orange. You start from A and you draw to the tail of B. And that's going to give you A minus B. Okay. And that works fine. This isn't the method I tend to use though. I tend to use the tail to tail method. For whatever reason, it I think it's a little bit more useful in physics, just because it's a lot of times when we're using these things to understand our vectors, it just comes up that that the tails are aligned, and it would be difficult to show a diagram where you flip the vectors, and you can show the difference of two vectors if their tails are already on the same location. So that's kind of what I want to show now. But the idea here is that instead of putting, the tail of B on the head of A, you put the tails. So we want to do A minus B. We put the tails at the same spot. So in this case, A going up and to the right, and then B starting at the same spot, but just going horizontally to the right, like so. Now, the point there is that, those are not being added. They're just two vectors at the same spot. But it turns out that if you draw from B to A, that vector is going to give you A minus B. Okay. So the idea here is that then notice that this vector right here is A minus B. And notice, within the realm of accuracy for freehand drawing, they're basically the same vector. Okay. So that's what's going on with that. All right. Now, as it turns out, I think the usefulness of this process is of graphical adding and subtracting vectors is limited. I think the analytical method is much more useful because it can give you numbers and it doesn't rely on you getting these drawings exactly right, pulling out rulers and protractors and so on and so forth. So I'm going to talk about the analytical method now. And the idea here behind the analytical method is simple. Basically, what you do is you break the vector into components. So your X and Y components. You can have three-dimensional vectors. We're not going to deal with those, but that is something that is within the realm of possibility. You break your vector into components, and then you add or subtract components separately. Okay, so the idea here is that if we have a vector A, and this is just written as A sub X comma A sub Y, and we have a vector B, which is B sub X and B sub Y, and finally we have a vector C, which is C sub X and C sub Y, and these vectors follow the relationship that A plus B is equal to C. The idea is that this says two separate things if the vector's in two dimensions. It says basically that AX plus BX equals CX, not CY, CX, and AY plus BY equals CY. Okay, so I want to show a couple of examples of looking at that. So we'll look at this. But let's just go with just an example one, just so we can go through this. Let's say we have a vector A. Tell you what, let's do a displacement. Let's say this is delta x1, and let's say this is 4, -3. We can say it's in meters. And then we have delta x2, and that is -6 and 10. Okay. And then delta x total is going to be delta x1 plus delta x2. All right. And the idea here is that basically what's going on is that delta x total, all we really need to do is we can break this into two components. And we're just going to add the first term, the 4 and the -6. So 4 plus -6 for the x component. And then we're going to do -3 plus 10 for the y component. And what we get when we break this into a vector is we get -2, 7. Okay? And that is what we get for that one. Now, it's helpful to draw, so this would be in rectangular form. Delta x total, whoops, not delta total, but delta x total. In rectangular form would be that. Now, if we were asked to do it in polar form, we don't necessarily need to draw it, but a lot of times it can be helpful to draw it. So I'm going to go ahead and draw it just to indicate kind of what's going on here. Now, what we have here is we would have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So we'd go -2 in the x and 7 in the y. So it would look something like this. Okay, so that would be delta x total right there. Now, if we want to get this as a if we want to get this as the magnitude, so we want to put this in polar form. The first thing we want to find is delta x total, the magnitude of that. Now, what you could do is graphically you can see, okay, basically what this is a triangle with 2 and 7. But it turns out that for the purposes of what we're doing, it doesn't matter if we use -2. Just use the x and y coordinates. So -2 squared plus 7 squared. And the reason is the square gets rid of the negative. So even though this triangle, it has a side of 2, the square will get rid of the negative and you get the same thing. So you end up with 4 plus 49. And that's going to end up being the square root of 53. So equals square root of 53, which ends up being 7 point something. You can calculate that. Not concerned about that. It's a positive number. Magnitudes of vectors will always be positive numbers. Now, here's the thing. If we wanted to find the angle, theta, well, that thing right there I've drawn is going to be theta. Now, the standard way you would do this is you'd take an inverse tan and you do y over x, because that's opposite over adjacent. So 7 over -2. Now, I suspect what you get is like a -74, something like that. Now, here's the problem. -74, basically, if we had, I'll do another angle phi, -74. Basically what that would mean is okay, instead of going in the positive direction, we go in the negative direction and we go 74. It's not quite to 90 degrees, but it would be down there. So that angle would be pointing, not quite the way I've drawn it, but that would be pointing in basically the opposite direction of the vector we want. Okay, so you might find that you get -74. But here's the thing. If you've drawn it, you know that -74 is a quadrant 4 angle. What you want is a quadrant 2 angle. So you want a quadrant 2 angle. Like we know from our picture that our angle should be giving us a quadrant 2 angle, and it's not currently. It's giving us a quadrant 4 angle. So if you find yourself in this situation, what you need to do is you need to just add 180. -74, it's -74-ish, plus 180. And what you should get is approximately 106. Okay? And 106 is a quadrant 2 angle. So that is the angle that we're looking for there. All right? I'll box that in. So you add -74 plus 180 should equal 106. And that is the theta you want. You don't want to use that -74 because this angle that you're looking at is not going at -74 degrees. It's going directly opposite that. Okay? So you got to keep that in mind. All right. Um, Last example I want to do is, let's say instead of this, we had a velocity 1 equals well, I'll tell you what, let's do it this way. Let's actually do a position 1. Position 1. So that's well, we'll say it's in polar form. This is 5 meters at 30 degrees. Okay. And then position 2 is going to be 7 meters at 150 degrees. And then what you might be asked to do is to find the displacement. Now, you might think, what's going on? Well, one of the things you can always do is you can remember that delta x is equal to x2 or x final. Actually, we'll do initial and final just for that. So it's equal to x final minus x initial. Okay. Well, that works just as well for vectors. Nevertheless, if you're going to do this, you need to convert it to a rectangular form, then change your components, and then convert back if you need to. Okay. So in order to do this, we convert to rectangular form to either add or subtract. Okay. The mistake people will make is they'll just subtract the magnitudes and subtract the angles. That's not going to work. That's going to give you something completely wrong. So what you need to do is we would need to say, okay, x initial. In order to find this, what we do is we'd say, okay, as a reminder, the x component, and you can visualize this if you want to. We talked a little bit about this, but it's 5. It's cosine of the angle times the magnitude being the hypotenuse. So it's 5 cosine 30 and then 5 sine 30. This is something you can more or less remember. As long as your angle is being measured from the x-axis, then the x component is going to be your hypotenuse or your magnitude times cosine of the angle, and your y component will be your hypotenuse or your magnitude times sine of the angle. Your x final will be 7 cosine of 150 and then 7 sine of 150. Okay. Now, you may or may not remember these. Cosine of 30 ends up being, it's square root of 3 over 2. Sine of 30 is 1/2. That's fine. But if we were to do x final minus x initial, basically what this is going to be, it's going to be 7 cosine 150 minus 5 cosine 30. And how I'm getting that is I'm taking this component and I'm subtracting the component of the x initial. So that would be the vector there. And then for the y component, it will be 7 sine 150 minus 5 sine 30. Okay. So that is what is going on there. Okay. So, I'll let you go ahead and do those calculations if you want to see that. But that is basically what is going on. And then if you want to convert back into polar form, you can. You may be required by the problem, you may not. But that is basically how you would add and subtract these vectors. So that's going to be the main takeaway. Know how to combine these vectors in this way, know how to break them into components, know how to add or subtract them. Question I get occasionally, what about multiplying and dividing? Multiplication of vectors. If you're multiplying a vector by a scalar, it's easy. You just multiply the magnitude and or the components by that scalar, whatever, doesn't matter. If you're multiplying vectors by vectors, there are different ways to do that, and they're beyond the scope of this course, so don't worry about that. So that's basically what you need to know. But this bit of vector analysis you will want to know. Again, break them into components, add or subtract them, and know that in order to add or subtract, you have to break them into components. And then last thing, if you're given components, know how to convert that to polar form. Okay, so I'll even write those tasks. 3 tasks. 1, polar form. 2, rectangular form. 2, rectangular form to polar form. And lastly, 3, add or subtract vectors. And again, the key to adding or subtracting is that you've got to convert them to rectangular form to do it. Okay, so that is going to be it for this lecture. Thank you for joining me, and I will talk to you next time.